the last couple of slides that I had gone through last time had to do with a couple of problems, just to give you an idea of the type of problems that you will have, you could be faced when we're talking about performance and performance comparisons and performance calculations. So you have time, plenty of time to practice this. When I release the slides, you can look at those problems, try them, bring up any questions to the class. Also, some of the homework is going to have problems like this. And again, if you, after you try them, if you want me to answer any questions, I'll do that as well. So we will have plenty of time, but this is the kind of problems or questions that we're talking about. So we went through this one and this one as well, okay? And I wanted to show you a couple more. So another example is something like this. A compiler designer is trying to decide where, between two code sequences for a particular machine. So this is now the compiler has a couple of options how to translate high-level code to a sequence of assembly language or machine language, a series of instructions. And then the hardware designers for the CPU have supplied the following data. So there are three instruction classes, A, B, and C, and the CPI for these classes of instructions are different. So class A, the CPI or the clocks per instruction is 1. So it takes 1 clock cycle to execute one instruction if the instruction is in instruction class 1. If the instruction is in instruction class B, then it takes 2 clock cycles to execute that instruction. And if C, then it takes 3 clock cycles. Okay, so this is for some particular high-level language statement that is going to be translated into the assembly language or machine language of the CPU. So now the two sequences that are being considered are such that the first sequence takes 2 instructions from class A, 1 instruction from class B, and 2 instructions from class C. The other alternate code sequence employs 4 instructions from class A, 1 instruction from class B, and 1 instruction from class C. Then the question is, which code sequence executes the most instructions? Which will be faster? And what is the CPI overall for each sequence? So again, when you get the slides, try these problems, bring questions, but these are the type of problems that you'll be encountering, both here in the slides and the homework. Okay? So just to get you going, look at this table here. We have the CPI, the native CPI for the different classes. And we basically have an instruction count in sequence 1. We said that there would be 2 instructions from class A, 1 from class B, and 2 from class C. And the instruction count, or IC, that's what it means. Instruction count in sequence 2 is 4 for class A, 1 for class B, and 1 for class C. And just to get you going again, we're showing that equation, which you can use to calculate the CPU clock cycles that is related to performance and execution time as the sum of the particular CPI times the instruction count for a particular instruction class. So in this case, the index I of the running sum goes from 1 through 3 because we have 3 different classes of instructions, A, B, and C. Okay? So again, think about that, try it, and come back with any questions. Now let's look at a popular, very popular in specifically in technical marketing literature. And this popular performance metric is MIPS, million of instructions per second. Okay? And what we'll find, well, I'll tell you is that this metric specifically is deceiving because it doesn't take into account the efficiency of the CPI for instructions. Just because you can execute more instructions per second doesn't mean that your machine is more efficient or higher performance, because the instructions may be doing very little. So it's just a partial indicator, but it is very popular in literature, so we wanted to bring it up. And it's simply millions of instructions per second is the instruction count divided by the execution time of those instructions times the million multiplier. Okay? Now you could say that the CPU in this context, which is the execution time, is the CPI times the instruction count divided by the clock rate, such that the MIPS then becomes the instruction count divided by this ratio here, instruction count times CPI divided by clock rate times the multiplier. And finally, that simplifies to the million of instructions per second is the clock rate divided by the CPI times the million multiplier. But again, it's not complete because it doesn't tell you how much work is being done. It just says that you can execute many instructions, but it doesn't relate it to the actual work and the efficiency of the instruction set. Okay? So again, the problems more specifically is depending on the ISA. So if you have an ISA that has very simple instructions, then of course you're going to execute more instructions per second. But overall, your execution time may be longer because it may take more instructions to execute a given task or a given program. So it's something that is used, and again, it can actually vary inversely with performance. You could have a higher performance machine that shows a lower MIPS just because the instructions may be more powerful. So just should be aware of that. Another for those machines that have floating point capabilities, another metric is the MegaFlops, or million of floating point instructions per second. So it's very similar to MIPS, but instead of just talking about instructions in general, it's talking about floating point instructions. Know that a lot of, mainly in the microcontroller market, a lot of microcontrollers don't have floating point units. They are done with the floating point operations are done with software. But this is another metric that is used. Okay, we are going to take a very close look at the IEEE format for encoding floating point numbers, both single and double precision and quad precision. But for now, we wanted to give you a preview of how these floating points are encoded, and they are encoded in binary, such that if they follow this equation. minus 1 raised to the sign bit times a fractional part times a power of 2, which is part of the floating point word as well. So the floating point, what we encode in binary, are the fields S, F, and E. Okay? So again, S is the sign, E is the exponent, and F is the value of the fraction that is normalized. So we're going to take a very close look at that. So let's go back and go back to our discussion of evaluating performance. Okay. At the end of the day, what we want to do is look at the workload that we want to evaluate, run that workload in, let's say, 2 systems which we are comparing, and look at the performance. Okay, which one is better? You know, are they similar, and things like that. So we can use the best thing is to actually use test workloads that are representative of the application that the processor is intended to serve. So real world workloads. Okay. But this is difficult because how do you know that what you have is the most representative program of the application? Unless you have a very specific application. But if you are trying to cover a myriad of applications, how do you know that you have something representative? So models or benchmarks can be used, okay? Because they can be reproduced. Everybody can be running the same thing, okay? And that way, you know, another advantage is to avoid privacy issues and security problems. So part of an example of benchmarks is what is called the spec benchmarks. And this is a consortium of companies that are in the computing business, and they have put together a set of programs that can be used to benchmark processors and computing systems. They have benchmarks for processors. They also have benchmarks for connected computer systems or network computer systems, which are the spec web benchmarks. And you can run things, for example, response time for a specific system, different configurations, so 1, 2, 3, or 4 processors, and you can see what the response time, which is for a connected computing system, something that is important, and it's not just the actual execution time for the program, but also is the response time to the client that is connected to this computing system. And you can see how that response time changes for a given number of connections or a given configuration. So these are the types of studies that you can run using benchmarks. Here's a different metric. So here on the left we have response time. Here we have throughputs. Throughput in terms of HTTP operations per second for the different configurations given the number of simultaneous connections that the server is dealing with. So given how many clients it is serving. So benchmarks are very important, and it is a standardized way of running specific programs that cover a variety of applications representatively and get a consistent metric from machine to machine in terms of comparing apples to apples. So how do we summarize this, this performance? Again, if we're going to be measuring what matters, which is the execution time, or in terms of connected computing systems, response time and throughput, we can have different jobs and we can measure them in different systems, okay? And we can get data like this. Execution time is the best indicator of performance when it comes to an actual computing system that is running software. So here we can say that system A is 10 times faster than B for program 1 because the execution time of program 1 in A, system A, is 1, but the execution time of program 1 in system B is 10. And these are some unit of time, as long as they are consistent. We can also say that for program 2, system B is 10 times faster than A because it takes 100 to run in system B, program 2, and it takes 1,000 for system A to run program 2. Okay? So these are the types of comparisons that we want to be able to make to compare different options in computer architecture and organization. And usually they are expressed as proportions. So remember that performance is 1 over execution time. So they are expressed as ratios or proportions. And here we can say that the performance of B overall, okay, the performance of B overall is 9.1 higher than the performance of A. And similarly, we can say that the performance of C is 25 times higher than the performance of A. And that the performance of C is 2.7 times higher than the performance of B. Okay? Now, as we start talking about looking at performance metrics as the basis to make decisions, to make decisions to improve a specific design, or to look at 2 different options for a design to be implemented, we want to bring to your attention what is called Dahls Law. And before I go through the more technical specifics of what it embodies, it basically says this, which is common sense. Make the changes, adopt, do the things where you have the most return for your investment. Get the most bang for your buck, essentially. That's all that is saying, okay? So the actual textual version of Dahls Law is that the performance improvement to be gained from using some faster mode of execution is limited by the fraction of the time the faster mode can be used. In other words, if you have a mode of execution that is only employed 10% of the time, okay, and let's say that you improve that system, what is the most that you could improve it? Well, the most that you could improve it is to make that time 0, to make it instantaneous, So it doesn't take any time. You're getting it for free, but it's only used 10% of the time. So you could never get the overall improvement lower than 90%. Because even if you made that 10% zero, that improvement only applies to the 10%. It doesn't apply to the other 90%. So what does that tell us? That if I have two choices, where am I going to invest my efforts to improve performance? In the 90% or the 10%? Even if I can make an ideal improvement on that 10%, it doesn't buy me as much as if I made a, let's say, 30% improvement only on the part that is being used 90% of the time. Does that make sense for everybody? So that is what Dahls Law embodies. And arithmetically, we can say that the speed up or the improvement is the execution time for the task without the enhancement divided by the execution time for the task with the enhancement. So let's say that we are talking about making an enhancement to some part of the system. But that is going to be equal as well to the performance with the enhancement divided by the performance without the enhancement. The conclusion in the terminology of computer architecture of Dahls Law is that what you want to do is make the common case fast, improve on what you are using the most, because this will tend to enhance performance better than optimizing at a higher level some other case that is used more rarely. So again, the common sense wording is get the most bang for your buck. So some more equations that are related to Dahls Law are this. Let's say that an enhancement accelerates a fraction f of the task by a factor s, but the remainder of the task is unaffected. What would be the execution time with the enhancement? Well, it would be 1 minus that fraction, which is the part that is not being affected, plus the fraction that is being affected, divided by the enhancement factor times the execution time without the enhancement. So here in this equation, you can see clearly that the speed up is limited by the unimproved part of the program, the 1 minus f. Even if s is infinite, your speed up, and the f over s term becomes 0, you can never get rid of that part, 1 minus f. So from that, we can conclude then that this relationship here at the bottom of the slide, that the execution time after the improvement is equal to the execution time affected by the improvement divided by the amount of improvement. That is the f over s part, plus the execution time unaffected. The execution time is the 1 minus f part. So it doesn't matter what the improvement is, you are limited by this. So what do you want to do? You want to make f as large as possible, so 1 minus f is as small as possible, and then this factor dominates and you get the most overall improvement. That's what these relationships, although they are very simple, they are very insightful, and I hope that you can see that. So some examples related to Dahls Law. Let's say that an enhancement runs 10 times faster than original, but is only usable 40% of the time. what is the overall speed up of the system? Remember the relationship, okay? Remember the relationships. So you can solve by the speed up, okay? Which is the execution time for the task without the enhancement divided by the execution time for the task with enhancement. In this case, it will look like this. So the overall speed up is 1.56. Let's unpack this. Here we have the part that is not being affected by the improvement, because the improvement is being used 40% of the time. So F is 0.4. And 60% of the system is not affected by the improvement, 1 minus 0.4. And then this 40% is being sped up 10 times. So that becomes the F over S. And then you can solve for this ratio, which is the execution time for the task without improvement, so the old system, divided by the execution time for the task with the enhancement, the new system. So we see that the speed up is 1.56. Another way of looking at this is that the system has improved by 50%. The performance has improved by 50%, 56%. Rather. So the performance of the system has improved 56%. But we actually made a part of it 10 times faster. How come the overall system only gets faster 56%? Well, that is because what we made 10 times faster is only used 40% of the time. If it was used 100% of the time, then we would get the full 10 times faster speed up. But it degrades rapidly by the amount that is not applicable to that enhancement that you are making. So again, this is an example of the types of problems related to performance and related to Dahls Law. So another problem that you may see, we can improve a CPU speed by 5 without affecting the I/O performance for 4 times the cost. Okay. The CPU, now we're talking about a system. It has a CPU and an I/O subsystem. The I/O is used 50% of the time, and the CPU is used 50% of the time. The CPU is 1/3 the total cost of the system. Is increasing the CPU speed by 5 a good investment from a cost performance viewpoint? So we're going to, for a CPU that is used 50% of the time and is 1/3 the total cost, we can improve the speed by 5 times for 4 times the cost. Remember our relationship. We always go back to that. Okay? The speed of the system overall is going to be the part that is not used. This is the I/O, because the CPU is used 50% of the time and the I/O another 50. So this is the I/O, the 50% that the I/O is not being changed. The other 50% is being sped up or improved 5 times. So we get an overall speed up of 67%. Okay? 1.67. What is the cost of this new machine? Well, 1/3 the total cost, which is the CPU that we are improving, now with this enhancement is going to cost 4 times. The other 2/3, which is the I/O, is not going to change because we are not touching it. So that's 2/3 of the cost. And that gives us a factor of 2. So overall, we are spending twice as much on the new machine, okay? But we are not doubling the overall performance, okay? So it's not a good investment, okay? From a cost performance perspective. All right, so let's just wrap up the chapter and look at power trends. So I talked about the trend given Moore's law of speed improvement through the 90s and into the early 2000s, and then that's when we got above 1 gigahertz and we broke the 100 watt barrier, and the processors really got, well, hot temperature wise, and the cooling systems were massive, and they were much higher and bigger than the processors itself, and they had to use actual liquid cooling technologies and huge fans, and it was getting bulky and expensive. That's what we call the power wall. The power wall that was hit at that time, and if you have touched an incandescent light bulb of 100 watts, you know how hot that is. So at that point, the trend changed in a couple of ways. The speed over here, the clock rate, which is the blue line, flattened. It flattened to stay around the low gigahertz. We didn't continue the trend because we would be at much higher frequencies right now. And then at the same time, as devices got smaller, by keeping the clock rate somewhat flat and decreasing the device sizes and decreasing the power supply, the power has started to drop. Then the question is, how did we manage to improve performance at that point? Well, remember that devices are getting smaller, so we can put more devices at this point. To save the day, enters multi-core. Because if you cannot improve the performance anymore by making the clock faster, what you can do is keep that clock sort of constant, but just put more processors on the chip or more cores to get more done, even at the same speed. So this is a very important chart that highlights that in CMOS technology, which is what is used for processor design, power is the capacitive load, which is an aggregate of what the capacitive load abstraction of the chip is, times the voltage square times the frequency. What this says is that if you wanted to reduce power, the best thing to do is to reduce the power supply voltage. The problem is that through this time, the 80s, 90s, early 2000s, the power supply voltage went from 5 volts to about 0.9 volts. And since we're talking about silicon, CMOS technology, which is the inexpensive material, we cannot get that power supply much lower than 0.9 because we do have the physics of the material, the quantum work function of silicon, which says that transistors need about 0.7, 0.6 to 0.7 to turn on. So you have to have just a little bit above that 0.7 volts. With some margin for noise, that's where we land at 0.9. So we had done everything we could here with power supply, and now we have the frequency. Well, the frequency is constant. And by putting more devices, we do increase this capacitive load, but they are smaller. They are becoming smaller. The geometries are getting smaller. So even though we're putting more, the fact that they are smaller tends to keep this constant as well, and maybe make it a little bit lower. So that's where this lower trend comes in. Okay? So this is a very important and interesting chart. So some problems are related to power. An example, suppose that we developed a new, simpler processor that has 85% of the capacitive load of the more complex, older processor. So that could be because it's simpler, or the devices, the actual transistors are smaller in geometry, because the gate capacitance is smaller if the transistors are smaller. Furthermore, let's assume that it has an adjustable voltage so that it can be reduced 15% compared to processor B. And that results in a 15% shrink in frequency. So power supply swing does affect frequency, how fast you can, how fast the transistors can switch. What is the impact on dynamic power? According to this simple relationship, that power is equal to the capacitive load times voltage square times frequency. And suppose that a new CPU has 85% of capacitive load of the old CPU. That's what we said. And at 15% voltage and 15% frequency reduction. Let's look at this this relationship here, comparing the power of the new system with the power of the old system. So this term over here, we said that the new system was 85% the capacitive load of the old one. The new voltage is 85% of the old voltage, and that the frequency was also going to scale such that the new frequency is 85% of the old one. And here we have the power for the old one, just C old, V old square times F old. So we get rid of the variables, and we get that the new power is about half of the old one. So basically, we have, by only shrinking the voltage, which decreases the frequency as well, and simplifying the system, or the chip in this case, to reduce that complexity by just 15%, we get a reduction in power by half. Most of it comes from the voltage, which is a square term, but everything else helps as well. So that gives you an idea of how this equation works. And last but not least, here's a nice chart that you're going to get when when you get the slides, this is pretty much the end of the chapter. Just to close and summarize, this is the performance improvement from 1978 to earlier in this last decade, about 2012, 2013. That's not very long ago. And plotting the performance improvement of a number of systems that have come into the market, normalized and compared to a VAX system in 1978. This was a mini computer type when computers they were like the size of a desk. The VAX were. You can see running at 5 megahertz. It gives you some slopes of improvement during different times. So normally, obviously, the 90s fueling the .com. If you have, I guess in your case, it would be history to learn about that. 52% improvement per year. Then, mainly because of the power issues that I talked about, that slope has been tamed to about 22% per year after the early 2000s. So you can take a closer look at that when you get the slides. And again, a lot of the continuous improvement here is because of the multi-core, because the speed has been relatively flat between around 3 to 4 gigahertz. Okay. So I'm going to wrap up the chapter. And what I want to say is that the important things that we have covered as an introduction in this chapter. Moore's Law is still relevant. Maybe the slope is not as steep as earlier times, but it still is relevant. Important concepts that we discuss in this chapter: hierarchies and levels of abstraction. The instruction set architecture, which we're going to devote chapter 2 entirely to it, the most important abstraction that you will learn in this course. How to abstract a CPU and present a constant view to the programmer by being able to come up with different implementations that are transparent to the user. We discussed performance, execution time, and also we discussed the issues related to power. Those are the big ideas from this chapter.